So yes, good afternoon. Thank you for being here. And I know some of you may be debating whether to stay or go for lunch, but I promise I'll keep it short and sweet. So, malware. So when you think of Windows malware, for example, you may think of dynamic analysis. You may think of sandboxing, Cuckoo Sandbox, Geo Sandbox, etc. But when you think of Linux malware, so let's say malware that target the MIPS architecture, or maybe the PowerPC architecture, dynamic analysis may not be the first thing that comes to your mind. So, I'm Nikhil, and today I'll be talking about some open source technologies that will help you in automating Linux malware analysis. A little bit about myself. So I'm a senior engineer at Netscope. I primarily work on intrusion prevention systems and detection engineering. In the past, I was a malware analyst at Cisco Talos and VMware, where I did a lot of reversing and detection engineering and automation. In my free time, I like to play FPS games a lot, watch anime, and then go on short hikes, but I mostly just play games. Full disclaimer, so today's talk is the result of my personal research, and any views or opinions expressed today are completely my own and not those of any employer, past or present. So, today I'll first start by talking about the extended Berkeley Packet Filter, or eBPF, its principles at a high level and how it enables runtime tracing. Then I'll talk about a tool called Buildroot, which you can use to create lightweight Linux images for various architectures. And then I'll present the ELFEN Sandbox, which I developed to perform static and dynamic analysis of Linux malware, and then you can ask me questions. So, eBPF. So in a line, eBPF enables the safe execution of sandbox programs in the Linux kernel. This technology was first introduced in 1992, and then it was just called BPF. It was a register-based virtual machine that used a RISC instruction set with 32-bit registers. And its main purpose at that time was to efficiently filter network packets. So instead of copying over network packets from kernel space to user space, filtering could be done at the kernel level itself. And as hardware progressed, as hardware improved, an extended version of it was proposed in 2014. Thus, E, which stands for extended, eBPF. And now eBPF is more general purpose. So optimizations like using 64-bit registers and replacing jump true and jump false targets with jump true and fall through targets to better fit the CPU branch prediction logic. Today, the terms BPF and eBPF are interchangeable. The original BPF is now called classic BPF or CBPF. Now, this technology has been around for a while, and it's being used for many use cases. So the OG use case, which is network packet filtering. So if anyone of you have used TCP dump, it actually uses CBPF internally for its filters. If you have any system performance issues, then you can use eBPF to trace the source of it. I highly recommend reading the blog of Brendan Gregg or his book to learn more about that subject. Today, however, our focus is going to be on the tracing use case of eBPF. Now, eBPF is a core part of the Linux kernel. It allows you to safely extend the kernel's capabilities without having to modify the kernel source code or build and maintain a kernel module. For example, in this case, we have a process that wants to load BPF bytecode, and it does so using the BPF syscall. Now that bytecode goes to the in-kernel verifier, where some safety checks are performed, and then once those safety checks succeed, that bytecode is JIT compiled and then loaded at a given hook point. Now, eBPF runs in kernel space, so security is paramount. Any process that wants to load BPF must be privileged. So it has to be either root or have the cap_BPF capability. Now, it is possible to load BPF bytecode from an unprivileged process if unprivileged BPF is enabled, but such bytecode is subject to reduced kernel access and functionality. Now, the in-kernel verifier performs some safety checks. For example, no uninitialized variables are allowed in a BPF program or any infinite loops. So a BPF program must end. Any BPF program also cannot be arbitrarily large or complex. For example, there is a limit of 1 million instructions that can be explored during program analysis. An eBPF program also cannot directly access arbitrary kernel memory. It has to go through certain helper functions in order to guarantee consistent data access. Now, once these safety checks are done, the BPF program is hardened. So, for example, the memory that holds the BPF program is made read-only, and any attempts to modify this will crash the kernel itself. So, instead of allowing any manipulated programs to run, the kernel will choose to crash. Any constants that are present in the BPF program, those are also blinded in order to prevent any JIT spraying attacks. And there are also some mitigations in place to avoid Spectre-type vulnerabilities. Now, in the context of tracing, the concept of probes are especially relevant. So, a probe is a location in the code where instrumentation can occur. Now, instrumentation can be dynamic or it can be static. So, on the dynamic instrumentation corner, we have kprobes, kret probes, uprobes, and uret probes. Now, kprobes and kret probes are ways to dynamically instrument the Linux kernel. So, kprobes is a way to instrument an instruction at a given address, and that could be the start of a kernel function or maybe at a given offset within the kernel function. And kret probes are when instrumenting when the kernel function returns. Uprobes and uret probes are basically the user space equivalent of kprobes and kret probes. So they are used to dynamically instrument user space applications. Now, on the static instrumentation corner, we have trace points and user statically defined tracing, or USDT. Now, trace points are instrumentation that exist in the Linux kernel code itself, and USDT is the user space equivalent. Today, our focus is especially going to be on kprobes, kret probes, and trace points. So, to leverage a kprobe, we have to call the register_kprobe function and pass the kprobe structure to it. This will make a copy of the probed instruction, and the first byte of that instruction is replaced with a breakpoint. When this breakpoint is hit, the registers are saved and control is passed to kprobes. Now, some code is executed, and then kprobes single steps through its own copy of the probed instruction, and then some more code is executed. Code that executes before the probed instruction is called the pre-handler. Code that executes after is called the post-handler. Now, the reason kprobes executes its own copy of the probed instruction is because the original instruction has a breakpoint. And in order to execute it, it will have to remove the breakpoint, but that will open up a small time window when another CPU might zoom past that probe point. Now, this is a structure of a kprobe. So I've highlighted in green some relevant members. That includes the address of the probed point, the address of the pre-handler, post-handler, the opcode, which was actually replaced with the breakpoint, and the copy of the probed instruction itself. Now, to leverage a kret probe, you have to call the register_kret probe function and pass the kret probe structure to it. This will install a kprobe at the start of the kernel function. When this kprobe breakpoint is hit, the return address of the kernel function is saved and it is replaced with an address to a trampoline. Now, this trampoline basically contains junk bytes, so NOP instructions. And a kprobe is also installed at that trampoline address. So when the kernel function returns, control is passed to the trampoline address where the kprobe fires and some code is executed, the return handler. And when that's done, the instruction pointer is then set to the previously saved return address and execution resumes from there. Now, this is a kret probe structure. I've highlighted in green again some of the relevant members. So the structure of the kprobe, which is installed at the start of the kernel function, and the return handler code, the address to the return handler code. Now, kprobes and kret probes are supported on a bunch of architectures, i386, x64, PowerPC, MIPS, etc. Now, trace points are instrumentation that exist in the Linux kernel code itself. So these are written and maintained by kernel developers. And compared to kprobes and kret probes, they offer more stable interfaces. For example, if the kernel version changes, it is possible that the kernel function name might change or the order of arguments might change, but the trace point is very unlikely to change. However, if you want to instrument at a certain location where trace points are not available, then you have to go with kprobes and kret probes. Now, this is a declaration for a trace point. So I've highlighted in green, I I hope you can read it. It is shed_process_exec. So shed there is the subsystem name, and process underscore is the name of the traced event. And now this trace point is used in this function, exec_bin PRM. So if you see right at the bottom of the image, that's where the trace point actually lies. Trace_shed_process_exec. So if any handlers are associated with that trace point, if it's enabled, then those are executed at that point. Now this function exec_bin PRM would have been previously called by bprm_execv, which in turn would have been called by execv. So this trace point can be used to trace execv equals. Now the Linux kernel requires BPF bytecode to be loaded into it for execution. We have talked about kprobes, kret probes, and trace points, but you don't necessarily need to know about how to write BPF bytecode to actually use these technologies. There are many open source projects which have abstracted away that complexity. For example, Sysmon for Linux is from Microsoft, a very popular and powerful tracer. Same with BPF trace and BCC. However, today's MVP is the Ply tracer, which is a very lightweight and open source tracer. Now, the second technology, which is Buildroot. Now, Buildroot is a tool that you can use to create lightweight Linux images for various architectures, MIPS, PowerPC, etc. And then these images can then be emulated using QEMU. And the amazing part is Buildroot allows you to modify the images. For example, if you want to enable the debug file system, if you want to enable kprobes, trace points, then it is possible to add certain kernel parameters to do so. If you want to install certain utilities, for example, ransomware might use the shared library libcrypto.so. So then you can install OpenSSL in your Buildroot image, and that ransomware will execute to completion. Now, finally, I'd like to present the ELFEN Sandbox. So ELFEN is a Linux malware analysis sandbox. It is based from Django. For scalability, it also uses Celery workers and RabbitMQ. And for your benefit, it also has been Dockerized, so it should be very easy for you to set it up. ELFEN performs both static and dynamic analysis of Linux malware. There is a GUI as well as an API for you to submit samples and retrieve reports. Now, ELFEN brings together a range of open source technologies. So we have discussed the two biggest ones, eBPF for tracing and Buildroot for creating Linux sandboxes. And today, I have released ELFEN for public, so it should be available in that GitHub repository today. And you're free to clone it, find bugs, and maybe even contribute to it. So ELFEN supports the static and dynamic analysis of Linux malware for a bunch of architectures. So x86 64, aka AMD 64, 32-bit MIPS, little and big endian, 32-bit PowerPC big endian, and 32-bit ARM v5 little endian. So let's say that you have a ransomware that targets ESXi hosts. So then in that case, the x86 64 image will be brought up. Some randomized ESXi related files will be inserted into it at specific locations, and then the malware or the ransomware will be executed in that image. Or if you have maybe a APT malware which targets MIPS, big endian, then the MIPS image will be brought up. Now, ELFEN uses the open source tracer Ply. Now, this is a lightweight eBPF based tracer. It has only one runtime dependency, which is libc. And since Buildroot also generates lightweight Linux images, and Ply is available within Buildroot to be installed, so this combination has worked out great. Now, remember that Ply is lightweight, so it is not as powerful as other tracers like BPF trace. Ply only supports kprobes, kret probes, and trace points at this time. So now I'd like to show what ELFEN is capable of. So I already have the Docker system running in the background, and ELFEN at this point uses the basic Django server, so it should be available to you at port 8000 on your local host. So first, let's go through the submission process. And whatever I'm showing through the GUI right now is also possible through the API, but I'm just going with the GUI for now. So in this case, I'm going to submit a MIPS big endian Mirai sample. For those of you who don't know what Mirai is basically a botnet malware. Just going to submit it off. And the second box where it says upload dependencies is, let's say, for example, if you have a malware and it requires another file which has to be in the same directory as the sample that you submitted, then those files can be submitted through this box. Now, in this case, Mirai doesn't really have any other dependencies, so I'm just going to let it be. Execution arguments, if your sample requires execution arguments, usually you don't know that prior to analyzing it, but sometimes you do know, and then you can provide those arguments here. Now, an optional feature, which is userland tracing, this is done through the LD preload module, and usually LD preload modules can be easily detected, so I've just kept it as an optional feature. So it just traces some of the string-related functions in libc, but again, it's an optional feature. Submit it, refresh it while it runs, and in the meantime, I'm going to show two other analysis. So this one is for the family AvosLocker. So AvosLocker, for those of you who don't know, it's a ransomware that targets ESXi hosts. So in this case, this one is for AMD 64-bit little endian. And in this case, I already knew it actually uses command line arguments. So the first argument is actually the number of threads that the ransomware spawns. And the second one is a hard-coded location where ESXi files will be inserted at runtime by ELFEN. Now this is the console output. So you will see multiple instances of encrypting the keyword. So we know that there was some execution that has taken place. Now the first thing that I want to touch on is the detection part. So there are two kinds of detection that is possible, static and dynamic. So on the static detection front, you have YARA rules. So YARA rules are applied on the sample that you have submitted and any dependencies as well. So in this case, a YARA rule has triggered for the AvosLocker ransomware, and it has given a score of 100. Now on the behavioral detection side is where the real power of ELFEN is. So the first one, for example, the ransomware generic detector. So a detector in ELFEN is basically arbitrary Python code that looks at events that were generated at runtime and then makes a conclusion from those events. So in this case, the ransomware generic detectors saw that there were multiple file renaming events and thus concluded that it may have been a generic ransomware and gives a score of 30, which in the malware world, at least, it's suspicious. So usually 70 to 100 is where it is called malicious, 30 to 69 is where it's called suspicious, and 0 to 29 is where it's sort of benign sort of scoring. Now, ELFEN also generates memory dumps during the runtime, and YARA rules are also applied on those memory dumps. So in this case, for example, the memory dump, YARA rules applied on the memory dump have also found AvosLocker artifacts, and thus it has triggered. Now, on the static analysis front, a bunch of program headers, section headers, ELF headers are extracted from the sample. Kappa, for those of you who don't know, Kappa is from Mandiant. It's an open source tool again. So Kappa also is executed on the sample, and it has found that there's a bunch of capabilities in this particular AvosLocker sample. Now, also some features from the sample are extracted. So for example, the average entropy, blockwise entropy, and there's a bunch more, whether it's stripped or not, whether if it's bagged, etc. Now, on the dynamic analysis front, we have file operations. So we saw that the detector had found multiple renaming events. So if you search for rename here, you'll find those events right here. So this old path is what is the original file, and after the ransomware encrypted it, it has given it the .avos Linux extension. On the process operations front, now ransomware that target ESXi usually have the behavior that they kill any VM, any already executing VMs. So if you search for VM process kill, then you will see that the sample had tried to kill VMs before starting encryption. Now on the dropped files, so any files that are created during runtime are considered dropped files. So for example, in this case, you will see that there are a bunch of encrypted files. You'll see the .avos Linux extension. So you can download all these and then analyze it further if you want to do so. The readme for restore is basically the ransomware note. From the string side, so memory string, so I mentioned before that ELFEN generates a bunch of memory dumps. So this is basically GNU strings being applied on those memory dumps. Now I'd like to show another analysis. This is also for AvosLocker, but this has a small twist. So for example, if I show on the console, so this is the original sample for AvosLocker. Take careful note of this value, ELF64. Now I introduced a slight corruption. So if I go to the corrupted sample and check the ELF headers, you will see now that this shows ELF32. And that itself is enough to cause read ELF problems. It already shows that there is corrupt ELF file headers. For example, if you look at the original sample, you will see that it's possible to dump out the program headers. But in the corrupted sample, you'll see that it's not possible to do so. But ELFEN has some more open source tooling that will help with that. So in this case, there's an open source tool called ELFEN, which I improved upon a while ago. So ELFEN basically fixes these kind of corruptions and then does static analysis. But dynamic analysis, as you can see, it still works, even in spite of that corruption. But anyway, ELFEN can do that. ELFEN can detect those corruptions and then do static analysis. So in this case, if you look at the program header table, you will still find those. Now let's go back to the original Mirai sample that I submitted. Where is it? It's here. Okay. Right. So this is the MIPS big endian sample. In this one, what I want to take your focus on is basically the C2 address. Right, there you go. So 79.110.49.85 at port 9375. So if you go to network operations, we'll see that it originally reached out to the Google DNS server. Maybe the sample was trying to find the IP address of the system that it had infected. And then it continuously reaches out to the C2, 79.110, blah, blah. And then it continuously reaches out to it for the rest of its execution time. Now I'd like to go back to our slides and talk about future work. So right now, ELFEN doesn't have a lot of detection rules. So it has a few YARA rules, a few detectors. But I like all of you to look at ELFEN and write some detection content and, of course, contribute to ELFEN. Now, MITRE attack is obviously a big one in the industry, and it's pretty useful to analysts, so I'd like to include that in ELFEN reports as well. Now, we saw the Mirai sample, and we saw that it did not execute beyond reaching the C2. So I want to add networking capability to the Buildroot images so that such sample can execute beyond the point of just peaking out to the C2 server. And of course, as and when the need arises, I want to support more architectures which can execute the relevant Linux malware. And that's it. Thank you so much for listening. You've been a great audience, and I'm open for questions.